Okay, so I guess you all know this. Just a reminder. I do suggest you go to the recitations. They're going to be devoted to answering your questions on the exam. Tentatively, it's here, although we're still trying to get a larger room. Let's see if this works. It's going to be a little more convenient if it's in a bigger room, but it's not easy to get. Okay, so two other reminders. Homework 2 due today. Homework 1 will release the grades today. Office hours. So there's a lot of office hours this week. Please use them, especially if you have questions before the exams. I'm changing slightly my office hours today because we had to move the TA meeting. So I'm going to split it, and I'm going to have half an hour at 5 and then half an hour at 6. Tomorrow, as usual. Questions? No questions. Yes, question.
There's a hint on Piazza about the average winnow. Is there any way that we could elaborate on that about, don't think of it as a multi-intuitive problem?
So the hint was, I think, a message from Rohan a few days ago that basically said what you've done for perceptron should work also for winnow. So really what you care about is consecutive weight vectors. Don't think about for a minute how you got these weight vectors. Just think about the fact that these are consecutive weight vectors, and then the trick that you've used for perceptron should work also for winnow. Is that helpful? Other questions? And then, by the way, the only impact of this, whether you do it or not, will be efficiency. It's clearly important, as you will see if you don't use it, but in terms of results, should be exactly the same results. Okay, so let's move on if there are no other questions. So where are we? So we are talking about theory of learning, or prediction theory. And just to remind you the setting, so we have an instance space, we have an output space that I think about as plus or minus 1. We're making prediction with a hypothesis that maps instances to labels. We always think about having some distribution over x cross y. We don't know what it is, but we know there exists a distribution that governs the generation of the data. And we are given a set of samples drawn independently from this distribution. Now, given that we have this, we can define two types of errors. The true error, this is what we really care about. And for example, you can think about it as the weight of the event h of x is different than the label y, measured on D. Of course, we don't know that because we don't know D. And the empirical error, which we can measure, which is over the sample that you have, how many times h of xi was different than yi. This is really the observed error that you have. Of course, it's the same observed error. You can measure the observed error on your training data, if S is the training data. When you have test data, this is also what you will measure there. But it has to be clear that the empirical error is just an estimate of what you may see. Hopefully, it's a good estimate. And one of the reason we want to talk about theory is because we want to be able to understand the true error as a function of the observed error, right? So you see error on S, you want to know, okay, what does that mean on the error, on the true error? So that's the key reason we care about, we want to understand some theory of here. So again, the terminology is also important. So we talk about the function space C, the set of all possible target functions, and the set of all hypotheses, the set of functions the learning algorithms is exposed to and can use. This could be the same function, doesn't necessarily have to be the same function, and sometimes, as I'll point out, we don't really care about C, the function space. We assume it exists, we don't have to assume it exists. We care about the hypothesis space, the set of functions we are playing with, or our learning algorithm is playing with. So the first question is, can we describe or bound the true error as a function of the observed error? And the second question, can we learn functions in C? What does it mean? That we need a definition for that, and we'll get it in a few minutes. But basically, you want to know, someone told me that the target function is in this class. It's a conjunction, it's a disjunction, it's a linear threshold function, it's a CNF. Do I have a chance of learning it, given that I'm going to use these kind of functions? And the theory that we want to develop will allow us to say something about it. What do we know already? From what we've done last time, where we played, if you remember, we kind of pushed the example of conjunctions and did some small analysis on it. Hopefully we agree that we cannot expect a learner to learn a concept exactly. I remember the example where we eliminated and maintained x1 because we didn't have data that allowed us to eliminate it. So in general, there will be multiple concepts that are consistent with the available data. We always are going to see a very, very tiny fraction of all the examples in the instance space. And these unseen examples that you haven't seen, most of them could in principle take any label. So we have to agree to misclassify at least uncommon examples, those that do not show up in the training set. So again, remember, as you're running example, think about the case of this x1 that we couldn't eliminate because x1 was never on in negative examples. So that's one aspect, but we cannot expect it to learn the concept exactly. We will have to settle for an approximation of the true function. Moreover, even that may not always be possible, because it could be that the sample that we observed is not really a good sample, is not really a representative sample of what we're going to see in the future. As we said, there is a distribution that governs the generation of the data, but because there is a distribution, it could also happen that the sample that we've measured for training is actually different than the one we're going to be tested on. There is some probability that this will happen, and therefore, sometimes we can't even expect to learn a close approximation. So these two together basically mean that we have to think about two types of uncertainties here. The only realistic expectation is that with high probability, this is the second point, with high probability, it will learn a close approximation to the target concept. Right? So it will not be a perfect, it will just be a close approximation. It will not be certain that we will get this close approximation. Sometimes this may not happen. So basically we're going to carry with us these two uncertainties, and we're going to use this as a way to define what we mean by learning. So the definition is the one that is called PAC learning, for probably approximately correct. Probably and approximately are the two uncertainties that we have. We require that given small parameters, epsilon and delta, where epsilon is our error, how far the learned hypothesis is from the true hypothesis, and delta is the uncertainty in getting to error of epsilon. So with given small parameters epsilon and delta, with probability at least 1 minus delta, a learner produces a hypothesis that has error at most epsilon. That's what we want. That's what we want to get. And again, the reason this is even possible is the notion of the consistent distribution assumption. The fact that the distribution that governs the generation of our training data also governs the generation of our test data. And you can also think about this diagram that I showed here, which will remind you the example we played with last time. So let me give the definition of probably approximately correct learning with a few more details. So we consider a concept class C over an instance space X, and a learner L that is using the hypothesis space H. We say that C is PEC learnable. Already here you have to remember what is learnable? What's learnable is the concept class, a collection of functions. Is learnable by L using the hypothesis space H if for all functions in this concept class C, for all distribution d over x, for some fixed epsilon and delta, positive epsilon and delta, the algorithm L, when given a collection of m examples that are sampled independently according to D, produces with probability at least 1 minus delta a hypothesis that has epsilon at most, that has error at most epsilon. And we want this m to be polynomial in the relevant complexity parameters, 1 over epsilon, 1 over delta, n, which is the dimensionality of the instances, and the size of H. Let's just stop here and make sure that it makes sense at least. That the complexity parameters are the right complexity parameters. So we expect m to scale up with 1 over epsilon. If you want smaller error relative to the true hidden concept, you would have to pay with more examples. If you want to be more confident, this is the delta, that what you got is a good approximation, you'll have to pay with more examples. The dimensionality should also play a role here. If the hypothesis space or the instances are more complex, longer, you will have to pay with more examples. And the size of the hypothesis space also makes sense, because if there's a lot of possibilities to choose from, you'll want to see more examples to eliminate hypothesis. So that's the definition of learnability. And now I'm adding the last bullet, which is, so far I just talked about whether it's learnable or not, didn't talk about efficiency, and we can add a condition for efficiency if this learning algorithm L can produce this hypothesis in time that is polynomial in these complexity parameters. Okay, so just to summarize what have I said, I said we have two limitations on learning. One of them has to do with sample complexity. Basically, I'm saying that m examples, where m is polynomial in the complexity parameter, I want to be able to produce a good hypothesis. So essentially, this is an information theoretic constraint. Do I have enough examples? Do I have enough information in the sample to distinguish hypothesis H that is a good approximation of F? And the second one is the time complexity. Is there an efficient algorithm that can do it? Questions? No questions. So again, notice that we are saying here that to be PEC learnable, a according to the definition that I gave, there must be some hypothesis that is close enough to F. At this point, I'm assuming, therefore, that H, the set of hypotheses, is at least as large as C. Why do I have to do this?
Because if you have a hypothesis in H, you're not, I mean, that if you have a hypothesis that's not in C, you're not essentially predicting F.
Yeah, so basically, if C is much, much larger than H, there could be functions in C that I have no chance of approximating, right? Because there's no element in my H that could represent them, or maybe not even approximate. So in principle, we want H to be large enough so that we have a chance to be either consistent with the target function or close to be consistent. We're actually going to drop this assumption a little bit later and replace it with basically producing a good approximation in the training data. But at least the intuition of why do I want to have a large enough H should be clear. Notice also that the definition that I've given, the PEC learning definition, is worst case. We say that we want this to happen for every distribution. It's called the distribution-free assumption. I don't make any assumption on the distribution that governs the generation of the data, and for every target function in this class. You may think that this is a very strict assumption, but it turns out that actually it's a simplifying assumption in the sense that it's easy to say things using it, and once you drop this assumption, you don't gain a lot. So I'll make some comments on it later. But I want to first highlight, why do we want this theory? So I know that this is a section of the class that some people find too abstract, and why do I need a theory? All I want is just to run learning algorithms. But you do want a theory because when you have an algorithm, all you see is some observed performance. You want to know, what does this observed performance mean about future performance? That's what you care about. And hopefully homework 2 gave you some understanding of the importance of this, because you've seen that you trained on something, you got some nice performance, and then we gave you another data set, and I think you got pretty lousy performance. So this is important. We want to be able to develop this understanding. What is the gap between the observed performance and the future performance? When can we bound it? When can we say something about it? So that's one. And two, we want to know, what does this gap depend on? What are the complexity parameters that will help us shrink this gap when we need to? Okay, so first of all, what have we done so far in the class? We said we're going to try to learn a consistent hypothesis, right? So give me data, I'm going to try to learn something that agrees with this training data and hope for good. So let's try to first quantify, what does it mean, hope for good? So this is kind of our first implementation of the theory. And you'll see that this is very, very similar to what we've done last time in the context of conjunctions, but now it's general. So what can we say? So the claim is this: the probability that there is a hypothesis that on one hand is consistent with my training data, my M examples in the training data, and on the other hand, 2, has large error, has error greater than epsilon, what do you want this probability to be? As small as possible, right? Everyone agrees with that? So that's our goal here, right? So we learn from our examples. Let's assume that we manage to learn a hypothesis that is completely consistent with the M example. In real life, this may not be practical, but we're going to relax it a little bit later. But let's assume that we can do it so that we are consistent. We want to at least guarantee that this hypothesis is going to be good. What does it mean, going to be good? It has error that is bounded by something, epsilon. So we want the probability that something is consistent and has large error, greater than epsilon, to be small. And indeed, we'll show that it's less than 1 minus epsilon to the m. This is something that goes exponentially down with m, the number of examples, times the size of the hypothesis space. Later on, we're going to bound this. So let's first convince ourselves that this is true. And the proof here is really straightforward. Let's assume that we have this bad hypothesis, the one that was consistent but still bad. The probability that H is consistent with one example is less than 1 minus epsilon, by definition. Because it's a bad hypothesis, its error is greater than epsilon. Since I've seen m examples that are drawn independently of each other, the probability that H is consistent with the m examples is less than 1 minus epsilon to the m. And the probability that some hypothesis in H is consistent with this m example, just by the union bound, is less than the size of H times 1 minus epsilon to the m. Now, what do we want? We want, as we said, this probability to be as small as possible. This is where our uncertainty comes in. So I want this probability. Okay, so by the way, just a comment here. Note that all my arguments here does not need any assumption on the true f. All I need is that I have a sample from x cross y. Whether you want to call this sample as generated according to f or not, it doesn't matter. So we really, all our arguments here are relative to the distribution on x cross y. So we bounded this probability and we want to make it small. And we want to understand what should m be if we want to make it small. So we want this probability to be less than delta. So I'm writing this desiderata here. 1 minus epsilon to the m times size of h less than delta. I'm taking natural log of both sides. This is the same algebraic argument that I used in the last lecture. Now I'm giving a little bit more detail. So this is the log of this. I'm using the fact that you probably remember, that you've seen it at least, that e to the minus x can be written as 1 minus x plus other things that are positive, and therefore e to the minus x is always less than 1 minus x. I'm substituting epsilon for x here, and when I take log of this, what I get is that natural log of 1 minus epsilon is always less than minus epsilon, and therefore I can replace it in this inequality. Instead of ln 1 minus epsilon, I'm going to write minus epsilon, and this will allow me to easily isolate m from this, and what you will get is that m has to be at least as 1 over epsilon, as large as 1 over epsilon times log of the size of the hypothesis space plus log of 1 over delta. In order to guarantee that the probability that I will get a bad hypothesis is less than delta. So what have we shown? Basically what we've proven is this Occam's razor algorithm, or Occam's razor argument, that if the hypothesis space is small enough, because you can see that the size of m is a function of the hypothesis space, what I can get is that if I see enough examples with high probability, at least 1 minus delta, the hypothesis that will be consistent with these m examples will have a small error, less than epsilon. That's basically what we proved. Questions on this? Yeah.
Bound in the previous slide, the bound is really small, loose, right?
It's very loose. The bound is very loose because I'm using union bound. I probably wrote it somewhere that it's very loose, or here. It's a very loose bound. We can prove better bounds, but this is a very, very simple one-slide proof that already gives the idea of what is this gap a function of. And you can improve it, but conceptually, it's always going to be a function of 1 over epsilon, the size of h, or the log size of h, and 1 over delta. So constants will change, and a little bit other things will change, but basically, that's where the understanding is. So in these complexity parameters. For example, it already tells us something about what kind of hypothesis spaces we want. What kind of hypothesis spaces we want? Small, right? Clearly we want small because that will mean that we don't need to take a lot of examples, and we don't need to be consistent, or later on almost consistent with a lot of examples. But clearly there is a trade-off. We want small hypothesis space, but we want it to be expressive enough, as we said before, so that they can represent the target functions. Otherwise, we will not be able to achieve consistency or close to consistency. So there is a trade-off here. But let's just go back to where we actually started the class. What do we know now about what I call here the consistent learner scheme? What do I mean by the consistent learner? I give you examples. Try to learn something that is consistent with this set of examples. What we know now that it's an okay scheme, right? We show that this scheme of take your examples, learn a hypothesis that is consistent with M examples, is going to be okay. It will generalize well, which means it's going to have small error, less than epsilon, with high probability, at least 1 minus delta, as a function of the size of h. Okay, so again, I'm repeating this point for the third time. Why should we care? We care because we want to understand this gap between what we've seen and what we'll see in the future. And basically what we've done so far is we prove the validity of this very generic procedure. Draw a sample, try to develop an algorithm that works well on it, it will be good if M is large enough as a function of the complexity parameters. So let's take some examples, right? So, before that, I'm going to say the same thing again, right? So we have a sample of M example. We show that if M is large enough, consistent hypothesis is going to behave well. And large enough is this. M is larger than 1 over epsilon ln over h plus ln 1 over delta. The first example we've seen last time was of conjunctions, and I can plug in the numbers. So last time we did a very specific, concrete analysis for the case of monotone conjunction. We used the elimination algorithm to find the hypothesis that was consistent with the training data. It was very easy to compute. And then we showed directly that if we have enough examples, then H is close to the target function. So basically we showed that conjunctions, the class of all conjunctions, is learnable. And basically that's a scheme that we can use for any collection of functions that you care about. You draw the M examples, you show that if M is large enough, we know that if M is large enough, we can find a consistent hypothesis is going to be good. We just need to show that we can develop an algorithm that finds this consistent hypothesis. So by the way, last time we showed it directly, but we don't need to show this directly. We can actually go from the general bound that we developed and say, okay, how large is the hypothesis space for conjunctions? It's 3 to the n. We agreed on that a few times. Make sure that you agree with it. And therefore, I can just plug it in, and I'm going to say, okay, if m is greater than 1 over epsilon ln 3 to the n plus ln 1 over delta, I'm going to learn a good hypothesis. So in terms of sample complexity, everything is fine. For example, if I want to guarantee 95% chance of learning a hypothesis of at least 90% accuracy, so my epsilon is 0.1, my delta is 0.05, m, and if I have n, the dimensionality, 10 variables, I need to see at least 140 examples. Small number because n is small. If I want to go with n equal 100, the number is going to grow to 1100 examples because it's linear with n, right? You can see that. Basically, you can see it here. You can also see that it's linear with 1 over epsilon, but only logarithmic with delta. So if you just want to improve your confidence from 5% to 1%, it just goes but a little bit. Okay, so again, these are very loose bounds, but still it gives you some idea of how many examples you need to get guarantees. And you know, it doesn't matter how I learn here, right? It basically said, if you have a learning algorithm that produced a hypothesis that is consistent with what you've seen so far, you have these guarantees on what will happen in the future. Okay? That's basically the value of what we've done so far. Okay, again, we have now a theory, and I want to give a couple more examples. So here is a more interesting example, KCNN. This is a very expressive class of functions. Think about it as you have clauses. These are the li1 or li2 or lik, which is this or this or this or this or this or this. And then you have a conjunction of those. You want and over all these options. It's a very expressive class of functions. You can think about it if you want, not in the Boolean domain. You can think about the ors as pluses and the and as multiplications. And basically what you have here are polynomials. But it's easier to deal with it in the Boolean domain for a reason that you'll see in a second. But the same argument actually works also if you replace this by pluses and products. So can we learn this class of functions? So what do we need to show this? We need to find an algorithm, and we need to show that the number of examples we need in order to learn this algorithm, in order to learn using this algorithm, is small enough, polynomial in the complexity parameters. So here is what we're going to do. We're going to draw a sample, use our algorithm to find the hypothesis, and determine sample complexity. So let's start with the determined sample complexity. How many examples do we need? And is it going to be polynomial in what we want? So how many KCNFs do we have? Where is the K here, by the way? I didn't highlight this. K is the size of this clause, right? So I have each disjunction here is of size K. Okay? How many disjunctions do I have? Doesn't matter. M is not part of my complexity here. So how many functions like this do I have? Let's think about it this way. So the function is really a conjunctions of different clauses. I'm calling them here C1, C2 up to Cm. And each Ci is a disjunction of k elements. So the size I'm claiming is 2 to the 2 to the 2 to the power of 2n to the k. Why? Any suggestions? So first of all, let's think about how many CIs do I have? How many disjunctions of size k do I have? It's 2n choose k. So I have 2n variables, or n variables plus their negations. Right? So let's think about these 2n variables. And I'm going to generate a disjunction of size k. So I'm choosing k variables to put in this disjunction. So it's 2n choose k, which is the order of n to the k. If you write this down, you'll see that basically what you have is n to the k, order of n to the k thing. So now this is the number of CIs that I have. And I'm going to choose a subset of them and conjoin them to get the CNF. How many subsets do I have? 2 to this power. We talked about it maybe a week ago. If you have a set of size 2 to the k, or size s, the number of subsets of it is 2 to the s. So I have 2 to the 2n to the k, and the log of this is going to be just the power here, 2n to the k. Which means that the log of the size of this hypothesis class is polynomial in n. Okay, so I'm fine in terms of sample complexity. What I have is something that is polynomial in n. So, from a sample complexity perspective, I'm fine. I have a pack hypothesis. All we need now is to develop a learning algorithm. Right? So I already know that if I manage to develop a learning algorithm that is consistent with my sample, I'm going to be fine. The future is going to be good. The hypothesis is not going to make too many mistakes. But what's going to be my learning algorithm? The one that will be consistent with the M examples. Okay, so now we are with the theory backing us. We just need to take the examples and develop a learning algorithm. What will be the learning algorithm that you would propose if you want to learn a function in this class? Decision tree would perhaps work, but we will not know that it works. Because notice that the reason my sample complexity worked is because I learned with hypotheses that are KCNN. Right? So I counted the size of H, which is the size of KCNF functions. If you learn with decision trees, I'm not going to get a KCNF, I'm going to get a decision tree. And the number of decision trees is going to be much, much larger, and therefore this sample complexity argument is not going to work. So that's a very, very good attempt here, right? So we know that we have a learning algorithm that is probably going to be consistent with the examples, right? Because decision trees can be consistent with everything. But this algorithm is not going to guarantee future behavior, because the hypothesis space of this specific algorithm is way too large. Okay? So here we get that this kind of the right trade-off that I wanted to discuss. You can learn with it. I cannot give you any guarantee. You may get lucky. You may not get lucky. In fact, it's completely clear that we can generate for you a sequence of examples that will make sure you're not lucky. I don't know if this is realistic or not, but it's possible to do. So let's go back and say, no, I want to learn, but I want to learn into this hypothesis space. I want to learn something that will produce KCNN. Ideas? Okay, so the hint is that it's hard to do if you only think about KCNF. It's going to be easy to do if you do transformation of the feature space. So what kind of transformation can you think about? Instead of your x's, if you were to suggest a transformation of the x's to another feature space, what would your feature space be? We've actually done something like this before. I think you want to choose these disjunctions as your feature space. Right? So instead of working in the space of the xi's, work in the space of disjunctions of size k over the xi's. So that's what we're going to do. So I'm going to my new features are going to be these yj's. Each yj is going to be a disjunction of size k. You see? Size k here. I know that there aren't too many of these because we already said just a couple of minutes ago that if I have n variables, the number of disjunctions of size k is order n to the k. I'm going to write down all of them. Now I have a new feature space. What is my target function over the new feature space? It's just conjunctions. Right? Over the new feature space of all disjunctions over size k, the new function is just a conjunction of these, of some subset of it. And I know how to learn conjunctions. So what have I done? I basically said I transform my feature space, and now I can learn, in fact, it's actually monotone conjunctions even, over this new set of literals. Here's an example, just to make this concrete for us. So let's assume that n is 4, k is 2, so all my disjunctions are going to be of size 2. Here is an example. This is going to be my y1, x1 or x2. My y2 is going to be x1 or x3. y3 is going to be x1 or x4, and so on. I didn't even show in this example any negations, but there could be negations. Okay, so this is the yi's are my new feature space. Okay? Now, if my original example was all zeros with some label, or 1, 0, 1, 0 with some labels, I'm transforming now the new examples to a 6-dimensional space. I'm showing here only the example of monotone disjunction, so it will be simpler. And it's easy to see that in this case I just have 6 examples. It's 4, choose 2. N is 4, and I'm choosing any 2 of them to put them in my y space, to put the disjunction of them in my y space, so I get 6. So the example 0, 0, 0, 0 translates into this. This example translates into, let's see, so my y1 is x1 or x2, so it's on because of x1. My y2 is x1 or x3, also 1. My y5 is x2 or x4, x2 or x4, and that's why 0. So the only one that is 0 in this example, that is the transformation of 1, 0, 1, 0, is this. Is it clear what I'm doing here? What is the transformation? Now I have a question. Question about distribution. I started with some distribution over the feature space X. I don't know what it is. I know that there was some distribution. The distribution over the new examples is going to be different. Now it's a new space, 6-dimensional space. There's going to be some distribution. Now, any distribution could have been the original distribution over the 4-dimensional space. Could any distribution be a distribution over the 6-dimensional space? When I said that any distribution, I could start with any distribution over the 4-dimensional space, I mean that every 4-dimensional example that you want could be there, could be sampled according to D. Is it true that any 6-dimensional example could be sampled according to the transform D? Yes?
No,
Why not?
because there will exist some examples in the 6D that are impossible given the 4D examples. Like if you have 2 and 4 off, then you can't have, like, if 2 and 4 are off, then the 2 and 4 will be off.
The mapping is 1, 1 not on to like every.
Okay, you're on the right track. Just 1 second. So basically you're saying there are some 6-dimensional examples that I will never see. Right, everyone? So give me an example of 6-dimensional example that I will never see. Yes?
0, 0, 0, 0, 0, 1.
Okay. Just the 6th element is 1 and all the rest are 0. Let's try. What is the 6th element? Is x3 or x4? So you say if this is 1, at least one of them must be 1, right? If, let's assume it's x3. If x3 is 1, y4 also must be 1. On the other hand, if it was x4 that was 1, y3 must be 1. So it cannot be that y6 is 0 and all the rest are 1s. The support on this example will be 0. So I started with any distribution you want, and in order to learn, I transformed it to another distribution. My learning algorithm really runs on the 6-dimensional space. So it runs on another distribution. Why is this important? Earlier today I said that tech learning assumes distribution free. So I'm not committing to what is the distribution that governs the generation of the data. And that's really an important thing, because if you were to develop algorithms that work only for one distribution, my algorithm only works for uniform distributions over my instance space, for example. That's going to be okay. I mean, you're allowed to do this, but this algorithm will have limitations. For example, I will not be able to use it in this case, because even if I started in my original space with uniform distribution, the resulting space after I transformed is no longer uniform. You just showed it to me. You just showed that there are some examples that you will never see, and therefore your only uniform distribution learning algorithm is not going to work. So basically the idea of developing learning algorithms that only work for specific distributions, while sometimes in some application could work because you know that the distribution that governs the generation there is limited, in general is not a good thing because of these things, because you want to sometimes you want to transform your space and then learn for various reasons, like the one we have here. We're going to see that again when we are talking about boosting, where again the idea is transform your examples, transform your distributions over examples in doing it. And if you only have boxes that know how to deal with specific distributions, you're limited. Okay, but what was my point here? Let's just summarize. I'm going back to the previous slide. We want to run our PEC learning okay. We want to show that the PEC learning algorithm, the PEC learning theory that we developed can be useful to show that this very expressive class of functions, KCNF, or if you want, polynomial, is learnable. To do this, we need to satisfy two conditions. One, sample complexity. We said we're going to learn this function using KCNF, and we're going to, by just using counting, we're going to show that the sample complexity is good enough, which means that if we learn using hypotheses in KCNF, and we manage to be consistent with our training data, the behavior in the future is going to be good. We can bound it, whatever epsilon you want. We're going to, with high probability, we're going to have error less than this epsilon. And we show this just by showing that the hypothesis space is small enough. Then we had to develop an algorithm that learns into this hypothesis space. That's a constraint that we imposed on ourselves because we want to be able to have a small enough hypothesis space. And the way to do this is we did a transformation of the space from the original n-dimensional space to an n to the k dimensional space. In the new dimensional space, in the new space, the functions we care about are simple. They're just monotone conjunctions, and we know how to learn. Questions? Yeah.
We will calculate m, right? In the next slide. So because
I actually did not calculate m here, but we know how to calculate it, right?
but so this it's possible that now if you try to calculate m, it's exponential because you change the hypothesis space. So now you want to learn monotone conjunctions over a space which is n raised to k.
Yeah, but it's going to be exactly the same, right? Because conjunctions, n to the k is a polynomial in n. So I didn't change anything. Think about it as n again, right?
You're not treating n to the k as exponential.
No, n to the k is polynomial in n. K is a fixed number. Okay, that's an important point. So the reason I call this KCNF, k is fixed. It's not one of my complexity parameters. K is 7, doesn't change. N, today I want n to be 10, tomorrow I want n to be 100. N is the dimensionality, which means it's my complexity parameter. K is just a fixed number. So therefore n to the k is a polynomial, and everything is fine. Of course, if you want the size of the disjunction to be a function of n, nothing I said holds. It becomes exponential. We don't know how to learn this. And in fact, my next slide is about negative results. I'm not going to give details here, but now that we have a theory, we can also show that some things are not learnable. And really there are two types of non-learnability results. There could be complexity theoretic that says, you know, I don't have enough computation power to do this, unless P equal NP or some other cryptographic assumption sometimes. Or I can give negative result based on information theory. I will never be able to see enough examples to isolate a good enough H. Or the number of examples I'll need to see to isolate a good enough H is going to be exponential in the complexity parameters. So just some examples include K-term DNF. Now, so we talked about CNF. For K-term DNFs, if you want to learn them using K-term DNF, you can show that it's NP-hard. Neural networks of a fixed architecture. Of course, we are all learning neural networks all the time, but theoretically, the class is not learnable. which means it's very difficult, if not impossible, unless you add some constraints to prove that even if you did something well in training, it's going to generalize well. There is now a lot of work on trying to develop generalization theory for neural networks, but the bottom line is that complexity theoretically wise, it's hard to learn. It's NP hard to learn neural networks. And a few other interesting concepts like read-once Boolean formulas. These are Boolean formulas where each variable appears only once in them. Also has some impact on Bayes nets learnability, because Bayes nets can be viewed with some massaging as Boolean formulas where each variable appears once. And we can also develop information theoretic non-learnability results. The most interesting one perhaps is deterministic finite automata. So if you have examples and you know that it's taken from a finite automata of polynomial size and you want to learn the finite automata, this problem is non-learnable. With the standard learning algorithm. With the standard learning algorithm that takes examples and tries to infer the automata. You can change the learning protocol. This is one of the interesting cases where if you change the learning protocol and go back to the learning protocols that we introduced a few weeks ago, where you can ask queries to the teacher and you can ask the teacher questions. In this protocol, actually, deterministic finite automata are learnable. But in the setting of using random examples, it's not. Okay, there are many other interesting examples here that I will not address. I want to see where we are now. So basically, I gave you a very quick notion of learning theory, but there are really two questions that are left. I mean, I really simplified it. I talked about completely consistent learners and showed that in this scenario is okay. And I talked about finite hypothesis spaces. H is part of our bound, the size of H. And I want to generalize to this. So I'm going to spend the rest of today and next time generalizing this. In one case, I want to deal with non-consistent learner. What if we learn from your M examples, but we're not completely consistent? We still make some errors. Can we still say something about the gap between our observed errors and our future errors? And the second is, what if the hypothesis class is not finite, right? This is going to be the interesting case because we don't want to learn just conjunctions and disjunctions or CNFs. We want to learn linear threshold functions. We want to learn other more general functions. And the bottom line is it's going to be okay. And the first thing that I want to say is about the non-consistent learner. This is something that we sometimes call agnostic learner. So we're trying to learn a concept class F using a hypothesis, but F is not in H. What does it mean? It means that when we use H, there's a chance that we will never be consistent with the data. Right? F is more expressive than all the functions that you can find in your hypothesis space. So our goal should be to find a hypothesis that has a small training error. Here is the training error. Before I called it error S. And I want to guarantee that the hypothesis with small training error still will generalize well, which means it's going to have good accuracy on unseen examples. This is my error D. So I'm going to give you some intuition for why should this work, or what are the tools that people use in order to show that this works without getting into the details. The key idea here is a probabilistic tool that is called hefting bounds that basically is used to characterize the deviation between the true error of the true probability of some event and the observed frequency of some event. So assume I have a coin here, which I don't, and I believe that this coin is fair. I'm going to toss it 50 times, 100 times. Even though it's fair, it's probably unlikely I will get 50-50. I will get something, I don't know what, 57-43. And the question is, what's the difference between what you observe and what is the true probability? So if I will get 47 and 53, you can say, well, it's still reasonable to assume that it's a fair coin. If I will get 10 and 90, you'll probably say unlikely it's a fair coin. Something is fishy here. And this is exactly the tool. So basically, the bound said that the probability that the true error or the true probability of an event is greater than the observed probability, the empirical probability, plus epsilon, goes down exponentially with epsilon and with m, which is the number of coin tosses, which hopefully makes sense to you, right? So if you want to guarantee a small gap, you're going to pay more, and you need to see a larger number of examples. So that's basically the tool that we're using. We are observing, one second. We are going to think about, we have a hypothesis. We want to estimate what is the true error of this hypothesis. How are we going to estimate it? We're going to try it on our sample, on our m example samples. We're going to observe some error there, and we're going to say something about the gap between the observed error and the true one, and bound the true one as a function of this.
Yeah, m would be the number of times you actually got the event, some event to happen, right? I mean, m is not the total number of coin tosses, it would be the number of times you got heads, if you want to estimate the probability of getting heads. Because if some event is actually less probable in the true distribution,
the probability of
getting heads is proportional to the number of times you actually got heads in your empirical data.
yes, but it's exactly the same thing. If I have two values, head or tail, then the probability of observing head is 1 minus the probability of observing tail. So this is still the right.
This only holds for binary?
The way I'm presenting it here, it's true. It's like this. But you can actually generalize this. You can use Chernoff bounds, you can use Hepting bounds. Yeah. So basically, I'm using this tool in the following way. I'm basically saying, I have a hypothesis. I don't know what is the true error, but I know what is the empirical error. And I want to know how many examples do I need to sample and observe the empirical error on this sample, so that I can say that my true error is not more than epsilon away from it. So basically, the probability of the true error D here, on the distribution D, is going to be greater than the probability on the training data plus epsilon, with probability e to the minus 2m epsilon squared. Which means that, again, if I want this event to have a low probability, I need to use larger m. That's basically what it says. I can use the same algebra that I used before. I want this bound to be less than delta, just like we said before. And I want to isolate m from this, exactly the same algebra that we did before. I'm going to take log of both sides, use the same inequality, and I can say two things. One way I can write it is, what is the gap between the true error and the training error? The true error is going to be less than the training error plus something. And this something is, again, let's see if it makes sense to us. This gap between the training error and the true error is going to be something that scales inversely proportional with M. The more examples you see, the smaller the gap is. It's going to grow with the size of the hypothesis space, right? So if you have a larger hypothesis space, it's going to be easier to fit the data, and therefore the gap is going to be larger. It's not surprising that you can fit the data with very, very large H. And it's going to be proportional also to 1 over delta, the confidence within which you get this. So this is one way to think about this, but I can also think about it as, okay, so before I get to also, I want to point out that we kind of saw this already, this gap between these two things. You can think about this as I said, the error on the training data. You can think about this as a generalization, right? So it's really a function of the hypothesis space and inversely proportional to M. We're going to see this a few more times, but we actually have already seen this. So if you remember when we talked about online learning, I'm bringing here slide 76 from the online lecture. What we've seen is that I've taken the loss function component that we had and added a regularization term for it, something that accounts for the simplicity of the hypothesis. And I said then that I have two components here. One of them is a term that minimizes the error on the training data, and the second one is a term that forces a simple hypothesis. We thought about the thickness of the linear function in that case. So this is exactly the same story, and in fact, what we have here is the justification for why do we want to add regularization parameter. Why do we want to control the simplicity of the hypothesis? We want to control the simplicity of the hypothesis because it contributes to the gap between the error that we observe and the error that we want to bound, the true error. So here we have some theoretical argument, and we're going to see versions of it again, for why we want to control the simplicity of the hypothesis. Okay, so before I get there, I want to take the same bound that I had before, and I want to present it as a condition on the example. So this is exactly the same bound, I just isolated M instead of isolating epsilon. So I'm calling the gap between the true error and the training error epsilon, and I'm saying now that if I want an algorithm that returns hypothesis in H with the least training error, let's think about training error less than epsilon, with confidence at least 1 minus delta, I want to see these many examples. And again, you can see the same thing. So if the number of examples is going to be inversely proportional to the error I want, which is the gap between what I observe and what I want, the true error, a function of the size of H, and inversely proportional to my confidence. Okay, so basically, so far what we've seen is that learnability depends on the log of the size of the hypothesis space. If the log of the size of the hypothesis is polynomial, small enough, we're going to be able to learn once we have a learning algorithm that was good enough, not necessarily consistent, but good enough on our training data. And the one step that is missing for us to be more general is the hypothesis space. So far, it's a finite hypothesis space. But we can think about, for example, this as a hypothesis space. I want to learn rectangles. In this case, I have 2 dimensions, so I want to know whether someone can play in the NBA, and the necessary condition to play in the NBA is that they have a certain height less than 7'5", and weight less than, I don't know, 400 pounds. So they have to be somewhere in this rectangle. So I can give you positive example and negative example of this, and you will have to return a rectangle to me. Any suggestions for how to learn? Positive example, negative examples. What will be your learning algorithm here? Again, I'm giving you examples. I'm telling you it came from a rectangle in the XY space. Give me the algorithm. Give me an algorithm that outputs a rectangle. Gradient descent would be one way. What would be your objective function here? While you think about it, I want a simpler algorithm. I can do it with decision trees, but in order to use decision trees, I will have to discretize the measurements along the x, measurement along the y. Invent a learning algorithm. Don't resort to any learning algorithm that we've learned. I'm giving you positive example, I'm giving you negative examples. Give me an ad hoc algorithm that will give me the best rectangle. Yes?
You set initial values, so you're bound for y and you're bound for x. And if, say for example, if you're bound here for y and you get a positive example here, you increase your bound, or vice versa, you get a negative example here, you lose.
Yeah, something like that. So basically, these are the positive examples. For all the positive examples that you've seen, take the max x and the mean x of the positive example. Take the max y and the mean y of the positive examples, and make this your proposed rectangle. That's basically what you said. You just said it in an online fashion. And now if I get another example, I'm going to increase it. So essentially, I can learn a rectangle only from my positive examples by trying to find the smallest rectangle that contains all the positive examples. Everyone agrees that is going to do it? Now, is this a good learning algorithm? Can you say something about how well will it do in the future? No. You don't know how to say anything about how well it will do in the future, because the theory that we just developed, because without theory you can do nothing, and with the theory that we just developed, it's not going to work because there are infinitely many rectangles. So we need to generalize what we said earlier today to the case of infinite hypothesis spaces, right? So that's basically what we want to do now. We want to deal with infinite hypothesis spaces that account to the fact that, just like before, we talked about the size of H, and we agreed that small h's are better than large h's. Now everything is infinite, but still there's a notion of small and large, right? So there could be infinite small, like rectangles, and much larger infinite spaces, say all convex polynomials. Right? They're going to be much, much larger than just rectangles. So I want to be able to quantify to quantify the size of hypothesis spaces that are infinite, and as a function of that, give you a learning theory that will allow you to say, yes, I can learn rectangles, but maybe I cannot learn if all polygons are in my hypothesis space, rather than just polygons with 4 sides or k sides. So that's what we're going to do next time. Questions? Yeah.
If I move to the late days, would they be deducted by hour on an hour basis or a day basis?
I don't know yet if we can technically do hours or not. So this is under investigations of the TAs. I hopefully will know today. So I don't have an answer.
Can you just post it on Freelancer and never?
Yeah, once we figure it out, we'll post it. If someone knows the solution, let me know. Okay, see you Wednesday.
If you have an infinite hypothesis class, the only way to learn is using an iterative algorithm, right? Or there are other ways to do it.
No, think about linear regression functions, right? You can use linear programming for them. I'm not saying it's the best way, but it's possible. So really, you don't want to use a batch algorithm because you typically need a huge number of examples, and computation is going to be hard, but it's possible.
I was just thinking about what theory we'll derive next time, so that's why I just assumed.
So the theory we derive is VC dimension. It's not algorithmic theory. It's basically for sample complexity. So it's actually a very nice theory. So I'll just spend one lecture to say something. Have you seen it?
Yeah, I've heard just briefly, but I'm not exactly well.
Yeah. It's a nice thing. So we'll just give a brief introduction.
One stupid question. I don't know why we need to multiply the size of the hypothesis when we calculate I know 1 minus epsilon to m is.
Yeah. I understand your question. So think about it this way. Just a second. So if I have many hypotheses. For this hypothesis, this one, I showed you that the probability that it is bad is 1 minus epsilon to the m. For this hypothesis, I also showed it. For this hypothesis, I also showed it. Altogether, I have, say, k hypotheses. So the probability that one of them will need this is this plus this plus this plus this plus this.
So the total possibility may be bigger than 1?
Yeah, it's always a union bound. Let's assume that I have 3 coins, okay? 3 dice. Let's do dice. What's the probability that this dice is going to give me an even number? A half. What's the probability that this dice will give me an even number? What's the probability that this one will give me an even number? What's the probability that any of these will give me an even number? It's not 3 times half. You can do it much better than this, right? But it's some kind of a sum of this, right? It's much larger than a half, right? You see that? So the way really to compute it is to reason a little bit more carefully. This will not give me a half with probability a half. This will not give me a half. So it's going to be 1 minus a half to the third. It's a much larger number than a half. But a very easy bound for it is to sum them, to say these events are completely independent, and therefore the probability that that one of them will give me even number is the sum of the probability. This is a very loose bound. But it has to be clear that the probability that one of them will do this is much larger than the probability that this one will do it.
So what the meaning that we calculate altogether is very loose?
It's very loose. It's very loose. Because I don't know how to do it otherwise. Because in order to not just sum Sum does disregard the fact that there's overlaps, right? In the case of the three dice, there's overlaps. That's why it's not just the sum, but I can account exactly to the overlaps. In the general case, I cannot account for the overlaps. I don't know the relations between the different elements in the hypothesis space. So the only chance I have is to say, okay, it's definitely less than the sum. Okay? I'm assuming that they are independent, so it's the sum.
So it's the estimation to the maximum.
Yeah, it's
size.
definitely less than the sum. And I'm bounding it by the sum, that's why it's a very, very loose bound. It's called the union bound, and you've kind of seen it in probability when you've seen multiple events, and the probability that one of them will happen is less than the sum of any of them will happen. Okay?
And one last question, sorry. For like, next you showed an example that it has estimate, I think, on the n to the k to n to I don't understand why it's 2n to the k. What was that?
So, do you agree that there are n to the k different disjunctions? Order n to the k?
Does disjunction use this for?
No, it's this. So I started with saying how many are there x1, x2, xik.
Why is not single k?
No, this is n to the k. But n to the k is about n to the k.
And then one by one will decrease by 10. I can keep on making it. I mean, I can just make phases up.
What is n to the k?
Potentially every pixel, every one cross one pixel could be
Minus
equal to k.
k.
So there's nothing to factually learn.
Right, another way of writing it.
Or it would just find that everything is 1.
And like this?
Yeah, but
I don't know how to
Yeah,
say it.
but you can also write it as n,
But right now I'm just giving
n minus 1,
Yeah.
n minus
nothing
k
to learn
1
all the scales.
divided by 1.
No. So I don't, because I think potentially.
So how many n's do you have
Give me a
here?
confirmation, I can make an photo out of it. I
Yes.
can make a phase out of it.
So
From
it's
any
n to the
configuration.
k.
Even with 16 nodes,
Oh, the
just
n
give
to the
something,
k.
and I'll make it, and somehow make
So
it
you have
into
k times
that's a phase.
n here.
I think that's possible.
Okay?
Not sure.
If you open the parentheses, you get n to the k and other things. And this is just a constant. So it's order n to the k.
Like, what you are checking is if you go from random configuration to a higher scale system.
So
And
why it's
what the
2n?
Now I have a set. I have a set of sizes where s is n to the k.
That is,
How many subsets
basically, it's only going to let those pass.
does
What
it
you're
have?
saying is we should allow more things to pass. That
It
you
will allow everything to pass. I mean, it should allow. Because I think potentially everything.
So the number of subsets is
Right,
2
so,
to the
so what you're concerned is it won't allow everything to pass through the fish.
Yeah.
So it's 2 to the
Okay,
n
well, all
to
we're
the
doing
k.
is reducing
And because
the
of this, so.
But you have 2n to the k.
Yeah, 2n. Really it should be here 2 because I can allow optimization. But it doesn't matter if it's 2n or n.
Why it's 2?
Because if I have k variables, if I have n variables, including their negations, there are 2 to the 2n. Negation means not variable.
Oh, so it's in or it's not in, if I have
Exactly.
2 different,
That's the bound. But you see 2n to the k or n to the k is the same complexity.
okay, I see. Thank you so much.
Okay.
It's interesting. Something to try. I think we should probably try it before we start.